Hey everyone! So, building a modern humanoid robot sounds like pure science fiction, right? Well, it's not. It turns out there's actually a pretty clear engineering roadmap, and today we're going to walk through it step by step. So, what does it really take? I mean, how do you go from a collection of motors and sensors to a machine that can actually think, that can perceive the world around it and make its own intelligent decisions? That's the big question, and that's exactly what we're tackling right now. We're breaking this whole thing down into four essential building blocks. We'll start with the absolute foundation, the robot's nervous system. Then we'll explore its virtual playground, a safe space for it to learn. After that, we'll equip it with senses and a brain. And finally, empower it to act on its own. It's a pretty logical journey when you see it laid out like this. All right, let's jump into step one, the robotic nervous system. Just like any living thing, before a robot can think or move or do anything, all of its individual parts have to be able to talk to each other. We're starting here because this is the absolute bedrock. Everything else is built right on top of this. And this communication backbone has a name. It's a framework called ROS2, which stands for Robot Operating System. Honestly, the best way to get your head around it is to think of it exactly like a central nervous system. It's the software network that's constantly zipping signals and commands between the brain, the sensors, and the motors. So, how does this nervous system actually work? Well, it's got a few key parts. You have nodes. Think of these as the individual workers, like a single motor or a camera. They publish what they're doing to topics, which are kind of like a shared message board that everyone can read. For direct commands, they use services. And the URDF file, that's the master blueprint. It's the file that literally describes the robot's physical body to the software. Okay, on to step two, the virtual playground. So our robot now has a nervous system connecting all its parts. That's great, but how do we teach it to actually use its body without, immediately breaking itself? And yeah, that's a huge problem. You can't just turn on a brand new, expensive prototype and just hope for the best. Real-world mistakes are pricey, they can be dangerous, and it's an incredibly slow way to learn. So, what's the solution? The solution is a digital twin. It's a perfect, super detailed virtual copy of the robot that lives and breathes inside a computer simulation. Engineers use these powerful tools, like game engines like Unity or simulators like Gazebo, to create these incredibly realistic virtual sandboxes for the robot to learn and train in. And the difference here is just night and day. In the real world, you've got expensive failures and physical danger. But in the digital twin, you have complete freedom. The robot can fall over 1,000 times, and it costs nothing. You can test new ideas in minutes instead of days, and you can run it through endless scenarios to make it smarter, faster. Okay, time for step three, giving the robot senses. Our robot has a connected body, and it's safely trained its basic movements in a simulator. Now it's time to take it out of the dark and let it actually perceive the world around it. And this is such a crucial point. Without perception, a robot is just a pre-programmed machine. It's completely blind. Perception is that magic ingredient that allows a robot to understand its environment and actually start making its own decisions. This is where AI really takes center stage, often using powerful frameworks like NVIDIA Isaac. It enables computer vision, which allows the robot to interpret the world through its cameras. It handles sensor processing, making sense of all that incoming data. And maybe most importantly, it allows for planning, using all that perception to decide what to do next. This brings us to our final and maybe most advanced step, from sight to action. This is where the nervous system, the virtual training, and the AI-powered senses all come together to create truly intelligent behavior. It all starts with sight. Using its cameras and computer vision, the robot takes in a flood of visual information about the world around it. It sees objects, people, and the layout of the room. But just seeing isn't enough, is it? Next, using multimodal AI, it connects what it sees to language and concepts. It doesn't just see a red sphere, it understands that it's an apple and knows what an apple is for. And once it sees and understands, it can finally take meaningful action. This is the moment it moves beyond just processing data. Now it can generate and execute a plan, using its motors and limbs to interact with the world purposefully. This powerful three-step process is called the Vision Language Action Paradigm, or VLA. It's the cutting-edge approach that finally connects sight, understanding, and action, unlocking a whole new level of autonomy for these robots. And this is the ultimate goal, VLA is what elevates a machine from a simple tool to a true collaborator, a robot that can genuinely perceive, comprehend, and engage with our complex, and let's be honest, often messy human world. So, as we've seen, building a thinking robot isn't a single magical invention. It's a methodical process, a combination of a nervous system, virtual training, and AI perception. The blueprint is here. It's moved from the pages of science fiction right into the labs of engineers. And so that leaves us with one final crucial question. The blueprint is here. The tools are being built. The real question now is, what kind of future will we choose to build with it? Thanks for watching.